Today, we will be investigating the fascinating relationship between the rotational speed of the ferromagnetic rod and the upward velocity of the neodymium magnets that are on it. The aim of the experiment is to explore how increasing the rotational speed of the ferromagnetic rod affects the upward velocity of the magnets. Let's begin by going through the apparatus we will use and the setup for this experiment. For this experiment, we will need ferromagnetic rods with varying diameters, cylindrical neodymium magnets with varying lengths, and a motorized setup to control the rotational speed. We'll also use a suitable method to measure the rod's rotational speed and a ruler to track the vertical movement of the magnet. We'll conduct a series of trials each time, changing the rotational speed and measuring the resulting upward velocity of the magnet. Other apparatus that will be used are a power supply, a stopwatch, and some other basic laboratory equipment. Now, let's discuss the principles behind this phenomenon. When we first look at this phenomenon, one may think that the magnet is being flung upward due to the rotation, and because it sticks to the rod, it keeps sliding upward. However, if you turn the setup upside down, the same phenomenon takes place, even when you spin the rod anti-clockwise. Essentially, when the ferromagnetic rod rotates, the chain of magnets rotates with it as well. This creates varying points of pressure on the magnet, which cause it to shift. In a nutshell, magnets shift due to a stick and slip phenomenon. Let us also take a closer look at the sound the magnets make when they're moving. It makes a sort of rumbling sound. This can also be seen in a violin bow, where if you drag it over a string, it sticks to the string, and if you pull it enough, it eventually slips and sticks again, ultimately leading to an audible frequency. And so the question arises, how does this phenomenon allow the magnets to defy gravity and climb up? For that, we must zoom into what is happening on the rod. So we have a magnified version of the rod and the magnetic cylinder. So basically, on a larger scale, if we look at it, the magnet slips when the rod is rotated and then sticks again. Slips and it sticks again, and this continues as it rotates. So now when it slips, notice how when it's stationary, the contact points are in the center from here to here. When it slips, the contact points shift to the left, to the right. They shift to this point and this point. And since the magnets are cylindrical, the contact points are now smaller than the diameter. Due to the moment of the weight of the magnets pulling it down from this side, the magnets fall down, and with this being the only contact point, magnets pivot about this point to climb up the rod. So they slip and they turn, they slip and they turn while they climb up the rod. So when the motion of the magnets is refrained to only the y-axis, there is still a small gap between the magnet and the y-axis due to the gap between the rod and the wall. So it slips slightly, touching the wall, then turns clockwise, slips again, and turns clockwise, and it climbs up doing so. The rotational speed of the rod can simply be concluded by the formula omega is equal to rotations upon minute. With the data collected from tracker, which is 31.5 rotations in every 15 seconds, we can conclude that the rotational speed omega is 126 r. So for the upward velocity of the magnets, we use the formula velocity is equal to displacement upon time. This gives us 3 cm upon 15.67 seconds approximately. With that, we can conclude the upward velocity of the magnet 0.1851 centimeter per second. With the two measurements collected, we can continuously vary the RPM and find different velocities, through which we can define a mathematical model in the future for the problem.